and he will be speaking today about modular groups over the Quaternions. Alberto?
Okay, thank you very much for the invitation. Maybe my talk is a little bit different than the other ones, more hyperbolic geometry than algebraic geometry. So I try to say it. Well, one group that we all love is universal. Since the time of Gauss, it has been one of the most fascinating and important objects in mathematics is the so-called modular group, complex modular group consisting of matrices, 2 by 2 matrices with integer entries and determinant 1, to be thought of divided by this. We're more concentrated in PSL to Z than proportion of that, like that. And it actually, the upper half plane, like this formula, we all know, one of the most all basic courses. It has application to number theory, to unity curves, to infinity many. So the modular group is one of its properties. It has 2 generators. One is this transformation, and the other is a translation. And the first T, acting on the upper half plane, is a rotation around of 180 degrees around I, the imaginary unit, and the other is simply translation. And the group generated by that is the modular group. And geometrically, we know that T represents inversion. Well, this is the same as saying it's a rotation around I. T has a fixed points, S doesn't have fixed points, parabolic unit. And if we consider as generators T and TS, we can show that these are also new generators. And they are free generators, and it can be shown therefore that the modular group is the free product of Z2 with Z3. Since we are to call the fundamental group of correctness of a laser space, projective space as laser space as one, you know, and más fuerte hablo. Bueno, muy bien. Perdón. Entonces, tiene 2 generadores.
En inglés.
No conozco alemán. Tenemos 2 generadores. And we have 2 generators, sorry, T and TS. And the ones for the 2, the ones for the 3. And therefore, we can show that this group is a free product of Z2 with Z3. That's another way of putting it. This is one of the most beautiful figures in all mathematics, in the tessellation obtained by this group. We all know, we use. And fundamental domain is this triangle here. Well, it's an ideal triangle, one vertex and infinity. So the angles are 60 degrees, 60 degrees. T is a rotation around I here, 180 degrees. And the other S component, which is a rotation of 120 degrees here. And then with this you tessellate the planes in this group. And therefore, if you take the fundamental domain and identify by the action of the group, you have to identify this side with this by that translation, and this half by that by the rotation of 180 degrees. You get the famous modular ortho. Is the manifold that parameterizes the unity curves. It's modular ortho. It's a fantastic object. And well, my objective, the objective of this talk, is to try to generalize this to the skew fields of Quaternions, the division algebra of Quaternions, and to surmount the difficulties due to non-group commutativity. And something has to be done. Well, therefore we consider as usual Blackboard H, the skew field of Quaternions. And as we know, obviously, like the university, we identify this quaternion with R4 in the obvious way. And here it's a little change with respect to the upper half plane. We consider in the in the space of quaternions, here, not working. I consider the set of all quaternions to real part is positive. You see, since we have 3 units, what we will choose I, j of k, there's no canonical choice, so we better turn our head 90 degrees and the upper half plane becomes the right half plane. And therefore, this is the object of study. Is the angle. So many times I will make a mistake, I say upper half plane, but this is what I mean. And in fact, upper half space, it's a 4-dimensional space. And well, we can, as usual, provide this space with the hyperbolic metric, which is that is metric. So this is a conformal metric. If you hit the metric divided by that, so since we know, and we all know that with this metric, the upper right half space, I would say plane, this half space, actually is a complete metric space of constant negative curvature equal to -1. And that's our model.
So you really have an embedding of the upper half plane,
By the way, for instance, if the space related by 1 and I is a copy of illusion, 1 and j is another copy, 1 and k, so we have 0. And in fact, if you take any unit, any complex unit, let's say ai plus bj plus ck, a squared plus b squared plus b squared plus c squared equals to 1, that gives you a copy. So it has many totally geodesic. So this is a trivial generalization. Anyhow, this is the universe in which I want to work. Right hand side, half space, consisting of quaternions of positive real parts. That's my. Now, of course, I want to construct a modular group, and therefore it's natural to consider the group consisting of 2 by 2 matrices, but now with quaternion entries. So it can be thought of as a 8 by 8 matrix with real coefficients. So I will say how. And so by this group, the G is the group consisting of these matrices with multiplication, the usual matrix multiplication, being careful not to commute. It's not commuted, so be careful. And the ones that are invertible. The ones that are inverted is equivalent to having unique terminal differences. Unique terminal is a generalization. Instead of the AB minus BC is a little twisting of that. But essentially, okay? So, of course, for any metric like that, in the usual way, we can construct the associated modular transformation. And the modular transformation is exactly the same format. Remember AZ plus B divided by Z plus D. It's the same thing, except, careful with the order, this is on the right, the inverse. I could have put that there. I have put A here, C here, made a mess. That's exactly the order I want. Okay? Careful, because things don't commute, and if you have mistakes like this, it can be really dangerous. So this is the method. Let's give you a complete excuse me? It's called a fractional linear quaternionic linear transformation. Excuse me? ¿Cómo? No. It's highly nonlinear. Highly nonlinear. Constant linear object, but it's highly nonlinear. In fact, it will be with a conformal transformation of the upper half plane. It's called a linear fractional. The fractional is the key. I should have called it fractional linear transformation, maybe. Or a Möbius transformation. That is the discussion. It's a Möbius transformation. It's probably a bit bad. The tradition of alphas called it like that. Okay, now, well, these transformations therefore act in quaternionic. But you know what? There's problems at infinity as usual, and therefore, if the one-point compactification of the quaternions, which since it's R4, compactification will be S4, and then in S4, with these conventions give them the same thing, the same ones as we use for Möbius transformations now. these Moebius transformations act for S4 with these rules. And the inverse is given by the inverse of dimension, so it's a beautiful group and many important properties. And the set of all transformation is a 2. Well, the map like that is on here. Well, let's see what's that. So, over here.
In the past, it was all the conformal.
Yeah, exactly. Well, what we have is that the set of full bits of that are exactly the set of different morphisms for S4, which are conformal maps for S4. And exactly like the
So it's all the conformal map.
exactly conformal and preserve the orientation. So it's fantastic. And
So what did you say in the previous one?
what?
In the previous one?
Yeah. What I'm saying that there's a map from the matrices to the Moebius transformation with in the previous case the kernel was also -1. In this case the kernel is the center diagonal matrix Ti like T real. Okay? Well, okay, so now when you have a unit ball, well, anyhow, these transformations, AQ plus B, multiplied with CQ plus B inverse, is a beautiful group. Depends on how many parameters? Well, depends on 16 parameters, A, B, C, D. But there's one condition, and then if you can see immediately that it has dimension 15. You have to take one parameter T. T times the identity, remember? 16 minus 1. And 15 is exactly the dimension of the group of isometries of hyperbolic space of dimension 4. So I make a very briefly resume. We explicitly give formulas of transformation of the sphere, S4, and one can show that this transformation actually preserves angles and orientation. And therefore it's a group of conformal transformation. Now, a conformal transformation on S4 has a canonical anything like that is a composition of inversion on spheres, of an even number of inversion of sphere. And therefore, Poincaré had this beautiful idea. This has canonical extension to the ball of dimension 5 in R5, and actually these extensions, called the Poincaré extensions, have the property of being isometries of the hyperbolic space of dimension 5. Reciprocally, any isometry of H5 extends canonically to the horizon, the bóveda celeste, as a conformal mapping. So therefore, this way we are intertwining hyperbolic geometry in dimension 5 and conformal geometry in dimension 4. A little bit like when Pedro was making stuff, that's the image I have. When you go to infinity, to the big bang, and then the scale disappears because of conformal geometry. So that's the picture I have. Maybe I completely wrong, but it's a natural picture. So on the other hand, the upper half plane, yeah, the Kelvin transform is the same as the unit ball. And well, we can consider therefore the set of Moebius transformations acting on the S4 that fit the lower hemisphere or the unit ball. And remember this formula? Remember this beautiful formula one learns in high school? Is in Russia, e to the I theta C minus K, 1 minus K bar Z. The function that takes a Z to that is exactly the set of Moebius transformation that represents this. It's a Moebius transformation. And so maybe we want something like that in the case of Quaternions. And look at this formula here. It's exactly the same thing, except Q is written on the left. Here, e to the I theta is a composite 2 unit quaternions, via Q. It's a little messy. And that's beautiful because that is the set of full transformation that preserves the unit disk is written like that. Anyone is exactly an analogous formula like that. Here we require that module, the absolute value of A is less than 1. We require here the same thing. And Well, this preserves the Poincare of the ball like that. And therefore, these transformations are what's given by this formula. It's exactly the same conformal transformation of the unit ball dimension 4 with the Poincare. Well, and this is our preliminary. So this is the Gauge transform. Notice it's a little different than the usual one. This takes the unit ball, the upper half plane, and the inverse of the opposite. And so we can go back and forth from the unit ball to the upper half plane. And so we have this. One transformation preserves the Poincare to the upper half plane. The other the Poincare to the this. So we're talking isomorphic things. There are isomorphic that they change one group from the other. We can go back and forth with one more than the other. But now we have the set of plane of Moebius transformations A Q plus B times C Q plus the inverse. And we want to consider the set of those Moebius transformations that present the upper half plane. For the case of the complex numbers, we know perfectly well that this means PSL to R. Moebius transformations, real entries in exactly the group that preserves. So we want the analog. What Moebius transformations preserve the upper half space. And that's what we want to do. Well, this has a long history. Alfors attributes to Carl Theodor Wahlen. He introduced very early in 1901 the idea of using the Clifford numbers to define Moebius groups of 2 at 2 matrices with entries in the Clifford numbers and to produce conformal mappings. And this paper by Theodor Wahlen, who was not a very good man, he's one of the founders of Deutsche Mathematik. There's an aspect of his life that is not very pleasant, but he did a very good theorem on and then Alfors, 7 years ago, took the idea of Wahlen and he started studying conformal mappings in higher dimensions. And so this is my idea. So this approach is also given by Página, and so my idea is to use the fact that the Quaternions is a Clifford algebra, but it's also a skew field, and so therefore things should be similar. That's what I want to do. But as it happens, the conditions given by Alfors were very difficult, very cumbersome, not very good. And in 2009, by the way, this work, before I forget, John worked with Juan Pablo Diaz, who's present here, and Fabio Lacci from Florence. So in 2009, Silvia Vinci and Graziano Gentili from Florence reformulated the conditions of Alford Parker and reduced them to a single relation, which is the following. A matrix A, AB, CD, with quaternion entries, presents the upper half plane if and only if satisfies this condition, where K is this matrix. So you just have to verify that. This is the transpose conjugate, the usual transpose conjugate. So one single condition can which Moebius transformations preserves the upper half plane or right half plane, half space. And we call these conditions the PG conditions, and these are equivalent to the Alfors Parker, but they are very efficient. Otherwise, we wouldn't be able to obtain what we have. So the proposition is this: the group of Moebius transformations which preserve the upper half planes is characterized by these three equivalent conditions. Instead of mentioning having this property that I mentioned, but also if you sort things around, is the conditions on the coefficients. So the real part of the product of that with part that, 0, etc. You can read it there. No? It's much more complicated than PSL2R. PSL2R is matrices with real entries and determinant. This is much more complicated, but and remember my objective is actually, I'm far from the title, I want modular groups. So now this group acts by orientation preserving conformal transformation on the boundary. So acts by isometries on the upper half plane. Remember, upper half plane is equal to right hand side plane, and extends the boundary by conformal transformation. And the boundary of the upper half plane having the point of infinity is S3, and we have this. Now, what I want to do is generalizations of the modular group, the reactive group. I'm in the first stage of that part. And things like that are actually very recent. There are papers by McLachlan, Waterman, Gillenberg, Johnson, but they just mention a little bit, they don't develop the theory reality. They're interested in other things. And also, Ruth Keller has some relations with hyperbolic manifolds, but with different aims. Well, now, I want modular groups. I want the analog of PSL to Z. So, what's the analog of Z? What are the integers in this universe? Well, fortunately, there's a canonical choice, first choice, are the so-called Lipschitz integers. The Lipschitz integers are the quaternions consisting of elements of this form with A, B, C, D are integers. Very natural. Actually, this is a ring of the quaternions. You can multiply them, you can add them, and this is a beautiful candidate. The segmentaries A, B, C, D, and A, B, C, D are Lipschitz integers. By the way, Lipschitz is based on that to prove that every integer is solved for number theoretical purposes. So that's what I want to know. I want to study this first case. And actually, the Lipschitz quaternions is a subring of a more important, impressive ring that I've heard when I was little. I thought was useless. It's beautiful. It's the set of all, is the Hurwitz quaternions. I mean, two great mathematicians invented that Lipschitz, which goes beyond the Lipschitz constant, and Hurwitz, that goes beyond the and consists of all quaternions where A, B, C, D are either all integers or all half integers. Mixed couples are not allowed. And all, okay, and you see that surprisingly is also is close on the multiplication and addition forms a subring of the quaternions. And actually the additive part is a lattice. And so I also want to study matrices with entries in the quaternions. And I have in mind other ones work in progress with algebraic numbers, with number fields, quadratic fields, and that hasn't escaped to us that can be done with on the progress. So this is what I want. So you can show, say, that the multiplication of two like that says subring of the quaternion. And the additive group is an example of a lattice. So the Lipschitz lattice is standard lattice. And the Hurwitz is you take the standard lattice and translate, add to that lattice, the lattice one half, add one half more of those. So the addition of two lattices becomes a lattice. So this is a very surprising thing. So I have this thing here. And now I want to know, little by little, what is the modular group. Because if I take all matrices with Lipschitz entries, that won't preserve the upper half plane. You have to have the conditions the BC Gentili conditions. And therefore, what we thought about, what about doing the same way we did it with the modular group? Namely, take translations by integer entries, and the equivalent to z equals to minus 1% and a rotation. And so we start by defining translation. So a translation is this, is a group, is a parabolic group. Like that. This is a more obvious Waves transformation, and because omega is pure imaginary, preserves the Quaternions whose real part is positive. So, and in terms of measures, are measures like that. Now we consider only translations where omega is the imaginary part of ellipses or curved integers. So now we have a group of matrices, a discrete group of matrices that possess the overlapping. Okay. The imaginary part of ellipsis integers is an ellipsis integer. I raised the first. But the imaginary part of a curve is not, because you should have a zero. You should have all half integers of all x's are integers, or all are half integers. So a purely imaginary is not, so you have to be careful. So we consider therefore the set for imaginary quaternions like that. And we have a subgroup of isometries consisting of measures, which are imaginary parts of Hurwitz translation. So that's the first approximation. This group acts freely. It's an abelian group with 3 generators. The fundamental domain is like a chimney, a little volume there. And then this the transformation z goes to -1 over z is now transformed to this transformation. This is a linear fractional transformation. This is the matrix that represents it. And this what makes the hyperbolic space a local symmetric space. It's a rotation of 180 degrees. It's an antipodal map. It's a radial antipodal map of S4. It's a rotation. And well, here we have all the properties, T. So the idea will be, I'll tell you now, the idea will be the modular group will be the group generated by, there are two groups, the Lipschitz group and Hurwitz group. The Lipschitz group will be generated by imaginary translations and D. And then I want to see how that. Okay, this is, remember the figure of the modular group. But this is the beautiful picture that we gave before I mentioned this. So the modular group will be. So if you could, so this is the upper half plane. We have the half sphere radius 1. So all this is like half space. This is a sphere of dimension 3. This is a hemisphere. And you take if the imaginary parts are free, take a standard cube and take place perpendicular to that. And that's the, so it's only a schematic. Well, with this already, you can build a beautiful group. Which consists of, as I told you, translations and that. And you start seeing the properties. And now it's beautiful because look at these properties. We have elements of order, or elements of order 6, elements of order 4. Now the group generated by this base, because it's not Z2 free products, it will be a very complicated group, has lots of torsion, and we will have to work a lot from the Cartel graph to find the generators and relations. But the geometry of that is really beautiful, this composition. So L omega is multiplication of T by the translation by omega on the right and the left. And you see the order depends, some have order 6, some have and then you start, you have to analyze all the different actions of these isometries. So there are rotations around totally geodesic planes of dimension 2, final rotation. Some are, so it's a very interesting geometry. I go fast now because it's a little longer. So now finally we get a definition. The ellipsis quaternion modular group is the group generated by the inversion T if the inversion Q goes to Q inverse, followed by translations by the imaginary quaternions to integer entries. Okay, that's a group. We call it PSL1. It's indeed a group, and the important theorem will be all matrices A, B, C, D satisfy the PG conditions are exactly this part of our group. This characterizes completely the group. It's a real modular group. Okay, it's a discrete group, and if we had taken all matrices in the Hurwitz group, we are wrong because that doesn't present the overlap plane. So it's very subtle. We have to do that, and that's what preserves it. And there's a nice group. It's the group of Lipschitz units. This is the group of, the Lipschitz ring is a ring, so which are its units in this group. It's a group of order 8, quaternionic group, right? It's not a linear group. And in particular, we have Möbius transformations by measures of this type, where U is a unit. And this group is a order 4, it's the Klein group, C2 plus C2. And we describe what the geometry of this group here. And now, a difference with the standard modular groups, but now we have a fine group. What's a fine group? It's a group of Möbius transformations that belong to the PSL2 Lipschitz, and which are affine, namely preserve all the holocycles, all the planes, horizontal planes at a given height. It's an affine group, and now this is what makes us. And this group is very beautiful. You see, for the modular group, this is trivial. No? This is only translations. 1, 1, Z, N, 1, 1, N. Translation by N is the only moment. The only thing that presents the horizontal line is translations, integer translations. But here is very rich. It's a very complicated group. Here. This is a direct product of C3 contains matrices like that. And in particular, in this we have to study the set of isometries, of affine isometries of the upper half plane, and these are very easy circled like that. Corresponds exactly to the point that preserves for the infinity. It's a new group of real dynamic. You see in the transformation that live invariant, the family of holospheres, parallel to the hyperplane of infinity. And this is a conformal group of R3. The conformal group of R3 is S of 3. It has dimension 7. Okay, so I will skip this. Okay, now I describe a Hurwitz modular group is the group generated by Hurwitz translations and T. And now these are, you see now the units of the Hurwitz group is this group. So you see it's a group of order 24. So in the field of quaternions, you have the Hurwitz units, and well, if you take these 24 elements here, they form one of the most beautiful objects in mathematics. Apart from the dodecahedron space, it's called the 24 cell. It's a Platonic solid dimension form. Not only the invariant on the multiplication. So you have this beautiful 24 cell. It's a polyhedron containing 24 vertices. It's a self one, You take the convex hull of this Platonic polyhedron. The faces are octahedral. This is really fascinating. This will play. This plays a role in the modular group. And actually, the classification by Felix Klein, the binary octahedral group. Anyhow, this beautiful object, you know all its combinatorial property, has it's a regular polynomial dimension 4, has 24 octahedral cells. Well, all information is there. And then you see now part of our theory will say how to do the faces of that to get an orbital of dimension 4, which will be an orbital of finite volume, and it's a hyperbolic orbital. And then if we are looking, we work hard, we take a Selber subgroup of that, Selber cover, and that Selber cover will be an actual manifold, hyperbolic manifold of finite volume. And therefore the ends will be tori, the costs will be tori, T3, and then if we compactify this tori, or maybe we get something. And the thesis of Juan Pablo, he obtains arithmetically the following. In S4, there is 5 tori, which are linked by the Borromean link, such that if you take tubular neighborhoods and remove them, what remains is a hyperbolic manifold, complete hyperbolic, like Forst's. And Forst's proved the opening of the figure 8. So this is but the problem, the thing is he does it arithmetically. There's an arithmetic procedure to do it. So this is working. What? ¿Qué dice?
No,
No está funcionando, ¿no?
ahora sí. Ya.
No, pero ahí. So this is the fundamental domain of our model. The first is not the fundamental domain. It's a part, subdivision of that will be the fundamental domain of the Lipschitz modular group, and another subdivision of that will be the fundamental domain of the Hurwitz group. So let me tell you along this. Okay, so these are just the way I describe the chimneys. So we give a complete definition of the fundamental domain. Now, if you claim that something is the fundamental domain, you have to prove that it's a fundamental domain. So part of the complications of the paper is, of our results, is to prove that this thing here will be actual fundamental domains. I think I put too much material in this. Let me see how I escape. Well, the polytope P, the chimney. So I mean, so this is R3, this is R4, half R4, and here I have an igloo. And I take, you see this cube here? This is the origin, and I take like that, and I intersect it with igloo, and that's the picture. Okay, but too many formulas but to explain such a thing. Okay. And actually, the fundamental cube, this cube, is divided into cubes. Anyhow, working hard, you find the fundamental domains like that. And I tell you what, with words, what I do. You saw the 24 cell is the complex envelope of the Hurwitz units. This can be subdivided into things that fit that. Like an Escher subdivision, which means that a subgroup of certain index of the Lipschitz group tessellates the 24 cell, and that's fabulous because now we will understand the geometry of these groups. So anyhow, this is the fundamental domain. What's the meaning of that? It's a cube in the hyperplane infinity. And then we have the walls, the cones, and so over that, over that, over that, over that. And those are the fundamental domains. I don't want to read all that. But we skip it, we skip it. Okay, so here, finally, one way to prove that those are the so the first lemma is that the real, you apply a transformation to cube. You see, this is a canonical formula for Moebius transformation. It also holds. But the fact that it's not non-commutative takes a, you see, this is the proof. It's a little longer. In fact, it's, you could guess that it was false. It's true. So this finishes the proof. So a little calculation with the formula is true, and then continue. And so this is the final unit. The Lipschitz modular group is generated by inversion in one is like I, and translations. And look at the relation. Now remember the field product of C2 with C3. Now look at this, it's fantastic. Element for the 6, elements for the 2, elements for the 4. It's a fascinating group, finite group, infinite group, which is a. Now, by the way, the number of relations can be reduced by and now the Hurwitz group is generated by the inversion around 1 and these translations here. And this is the relation. You can see it's a very complicated. And to prove that, I say like that, it's complicated. You have to actually find the Kelvin graph of that. And so you take the chimney, you subdivide it in little pieces, what I showed you. And these little pieces also tessellate. And now using that and the group action, you construct the Kelvin graph of the group, and looking at that Kelvin graph, you determine the group in a very, I'm going very fast, but that's a, well anyhow, now you have orbitals. You take the upper half plane divided by the Lipschitz group, and you have beautiful orbitals. And the important thing of that is that these orbitals, we give a thorough description of the model of the similarities, the isotopic groups, a complete, very long description and detailed description of all the properties of the solid. Very complicated. The model orbital has one singular point for the 2, one singular point for the 3, and a constant infinity. This is not. It's a very complicated, has a skeleton, very complicated stratification. We compute the volumes, they are all multiples of pi, rational multiples of pi. And then we have a beautiful theorem of Selberg saying that these groups actually have finite index subgroups that act freely, and therefore now we have not orbitals but hyperbolic bindings, an infinite number of new hyperbolic bindings, which are arithmetic, are given by formulas, no? Like the Solas formula. And we obtain this coincides with papers by Chance and Ivancic, and new examples of hyperbolic manifolds. They already finished. Something happened on the way to the formula. Well, anyhow, I think it's too complicated, but okay, so I will resume. I'm working with Moebius transformations over the quaternions. I have to be careful by saying the truth, like theater, no? I have to be careful how I write it. They don't believe it. So I write A cubed plus B, multiplication, C cubed plus D inverse. Now I want discrete subgroups play the role of the modular group, so I need integer entries. I have two choices for the moment. I have more than that. I have the Lipschitz integers and the Hurwitz integers. The Lipschitz integers are a subring of the Hurwitz integers. And now, doing that, we obtain the fundamental domain, we describe the corresponding orbifold, we construct this, the whole theory, and of course, many things come to mind. For instance, it's under construction. We are working on congruous subgroups. Many more examples of hyperbolic manifolds, Hilbert modular manifolds. Now that we have a definition of what we want, and we're working on Bianchi groups, we're working on many things. This is just the beginning, and it's very open. And I did it very fast because I didn't realize there was so much material. Okay, so better let you rest.
Any questions for Alberto?
Yeah, if the group is non-discrete, you expect to have some equidistribution.
If the group is not discrete,
Finitely generated but non-discrete,
yeah, of course.
you don't expect equidistribution.
I mean, there's the notion.
Right.
I mean, we are working also. There's the geodesic flow, and there's the holocyclic flow, the holocyclic foliations. You have a theoretical distribution theory, yes. You know, like the Riemann hypothesis reduced to a certain equidistribution of EFM to Z. Theory was again. And here you have an analogous. So you saw the chimney. Well, it's invariable in the translation. So if you take the orbifold, it becomes a torus. If you take a curve. So the costs are tori. You can think of the measure concentrated in this tori. If the height of the tori tends to infinity, goes to the quadrant infinity. But if the height tends to zero, this tori becomes more and more dense. Then to fill the orbifold, and the speed of the way you fill it is related to an associated zeta function of that. There's something like that. And of course, one question that we ask is, what about modular forms? And so far we haven't succeeded. For instance, you take the infinite product of 1 minus q to the 24, the canonical. Well, yeah, you can define it's beautiful, but it's invariable, it's not modular. But we're experimenting, why not? And but I think if the groups are you have the equidistribution.
Any other questions?